Look around you and imagine choosing 10 completely random people. 9 of them will probably prefer using their right hand. They write, eat, throw, and handle everyday objects mostly with that hand. These simple actions happen so naturally that we rarely notice them. But one person in the group may do almost everything with the left. And that's strange when you think about it. Our two hands look almost identical and can perform many of the same movements. So why isn't humanity divided roughly 50-50 between left and right? Instead, roughly 9 out of 10 people prefer their right hand. Somehow one side became overwhelmingly dominant across our species. This pattern has persisted across cultures and throughout much of human history. Yet left-handed people never disappeared. They still write, eat, work, and interact with the world using their left hand. So why has evolution maintained such an uneven balance? Every left-handed person represents a surprisingly persistent biological minority, and humans aren't the only animals that favor one side. Chimpanzees and other animals can also develop preferences for particular limbs. But humans show an especially powerful, population-wide bias toward one hand. Something pushed our species strongly toward the right. To understand why, we first need to look at how handedness develops. Your preference for one hand may begin surprisingly early. It starts long before you ever learn how to write. Young children can already show preferences when reaching for toys. They may repeatedly use the same hand during simple everyday activities. Even holding a spoon can reveal an emerging preference. And evidence of lateralized behavior may appear even before birth. Researchers have observed fetuses moving one arm more frequently than the other. Fetuses can also show preferences for sucking one thumb. Parents don't need to deliberately teach these behaviors. Their origins reach deeper into the developing nervous system. The first major clue lies inside the brain. From the outside, the two cerebral hemispheres appear remarkably similar. But they don't always divide their work equally. This specialization between sides is known as lateralization. For many movements, the left hemisphere mainly controls the body's right side. Meanwhile, the right hemisphere mainly controls the body's left side. This crossed organization helps explain how the brain controls our hands. But left-handed people don't simply have completely reversed brains. Human brain organization is far more complicated than that. Different functions can show different patterns of lateralization. Language provides a useful example. In most right-handed people, language processing strongly favors the left hemisphere. Many left-handed people actually show the same general pattern. Others distribute language processing more evenly across both hemispheres. So the popular idea that left-handers are simply right-brained is misleading. Being left-handed doesn't automatically make someone more artistic or creative. Complex abilities depend on networks working across many regions of the brain. Two left-handed people can therefore have very different talents and personalities. The brain is only one part of the handedness puzzle. Genetics also influences which hand you eventually prefer. But heredity doesn't work like a simple left or right switch. Two right-handed parents can have a naturally left-handed child. A left-handed parent can easily have a right-handed child. Family patterns change probabilities rather than determining a guaranteed outcome. Identical twins make this even more interesting. One identical twin can prefer the right hand, while the other prefers the left. Their DNA is extremely similar, yet their handedness can differ. So there is no single genetic switch controlling the entire outcome. Multiple biological and developmental influences appear to contribute. Think of biology as slightly loading a coin, rather than choosing the result. The coin can still land on either side. Small developmental differences may influence how neural connections become organized. Genes, brain development, and other influences interact during this process. The result can be right-handed, left-handed, or sometimes a more mixed preference. Yet none of this fully explains humanity's enormous right-handed majority. For another clue, we can briefly look beyond our own species. Chimpanzees can prefer one hand when manipulating objects or using simple tools. An individual chimp may repeatedly perform precise tasks with the same hand. Parrots can also favor one foot when holding food. The preferred foot can repeatedly perform the same specialized task. Cats sometimes show preferences when reaching toward objects. Dogs can also favor one paw during particular behaviors. Some kangaroo species show especially interesting preferences for their left forelimb. Their limb use demonstrates that population biases aren't uniquely human. Fish can even show preferred directions when responding to their surroundings. Birds may favor one eye when inspecting particular objects or situations. These examples reveal that lateralization exists throughout the animal world. But individual animals can favor different sides in different species and tasks. Lateralization clearly existed long before modern humans appeared. Specialized sides can help nervous systems divide and process different kinds of information. So our basic left-right organization has deep evolutionary roots. Different sides can specialize while still working together as one system. Yet humans stand out because our population is so strongly biased toward the right. Across a crowd, right-handed actions dominate again and again. That suggests our social evolution may also be part of the explanation. Imagine traveling back to a community of our distant human ancestors. One skilled individual sits down and begins shaping a stone tool. One hand stabilizes the stone while the other delivers precise strikes.
Like this? Can you show me one more time?
A younger group member carefully watches every movement. Then the learner tries to reproduce exactly what was demonstrated. The first attempt may be clumsy, but repeated imitation improves the technique. Teacher and learner now perform increasingly similar sequences of movements. Other group members can learn the same technique by watching them. Eventually, useful stone tools begin appearing throughout the community. Adults can pass successful techniques directly to younger generations. Children don't need to rediscover every survival skill from the beginning. Knowledge can travel from one pair of hands to another. The same principle applies to preparing food and performing other practical tasks. Coordinated movements can make shared work more predictable. Cooperation also became crucial during hunting and other group activities. Gestures and repeated actions helped individuals coordinate with one another. Shared movement patterns could therefore make some forms of cooperation easier. Groups also worked together to construct shelters and modify their surroundings.
Hold it like this.
Familiar tool use could make
understand.
demonstrating
Now, you
and
try.
exchanging
Take
skills
it
more
slowly.
efficient.
Yes, like this?
Perfect, you got it.
A useful technique discovered by one individual could spread throughout a community. Adults could demonstrate those movements repeatedly to children. Generation after generation, knowledge accumulated instead of constantly starting over. Tools, food preparation, shelter, and hunting all benefited from social learning. Human survival increasingly depended on learning from other people. In a sense, many connected brains became more powerful than one isolated brain. Communities could preserve knowledge far beyond the lifetime of one individual. Successful movements and techniques could spread across entire populations. Sharing a common directional preference may have made some interactions more predictable. Once one side became common, matching that majority could provide small advantages. Children repeatedly observed the dominant movements of the adults around them. Those children then learned and reproduced many of the same actions. The pattern could continue from one generation to the next. Over long periods, even small advantages can influence population-wide tendencies. A modest initial bias can therefore become stronger over many generations. Eventually, right-handedness could dominate, while left-handedness remained a minority. But now, we encounter the biggest problem with this explanation. Left-handed people have continued appearing generation after generation. Thousands of generations passed without eliminating the left-handed minority. Perhaps cooperation is only one half of the evolutionary story. Humans cooperate extraordinarily well, but humans also compete. Imagine two ancestors facing each other during a direct physical confrontation. An attack from the less familiar side might be slightly harder to anticipate. We can see a modern version of this effect in competitive sports. Boxing provides one of the clearest examples. Most fighters spend much of their time facing right-handed opponents. A left-handed southpaw changes the familiar geometry of the fight. Punches, defensive positions, and foot placement can arrive from different angles. The left hand itself isn't magically faster or stronger. The important difference is how familiar the opponent is with those movements. Facing opposite stances changes the angles between both competitors. A left-handed fighter regularly encounters right-handed opponents. Right-handed fighters also spend most of their time facing other right-handers. So, a rare southpaw can present a less familiar challenge. The minority gets frequent experience against the majority. The majority gets much less experience against the minority. Similar effects can appear in fencing and other interactive sports. Again, the potential advantage comes from unfamiliarity rather than superior biology. Competitors must adjust their movements when facing an opponent with the opposite preference. This principle can apply whenever opponents react directly to each other's movements. Left-handers can therefore be unusually represented in certain competitive situations. Being rare means constantly practicing against people from the majority. Meanwhile, majority members encounter the rare pattern much less frequently. Similar dynamics may have occasionally mattered during human evolutionary history. This gives us to evolutionary pressures, pulling in different directions. Cooperation can reward similarity, while some competition can reward being unusual. This balance leads to a fascinating evolutionary possibility. Imagine left-handedness becoming much more common in the population. Right-handed people would then encounter left-handed movements far more frequently. With enough exposure, those unfamiliar movements would become increasingly familiar. The special advantage created by rarity would begin to disappear. When left-handedness remains uncommon, however, unfamiliarity can persist. Evolutionary advantages can sometimes depend on how common a trait becomes. This general idea is called frequency-dependent selection. It may interact with genetics, development cooperation, and many other influences. No single explanation completely accounts for human-handedness. Culture has also changed how left-handedness appeared throughout history. In many societies, teachers and parents discouraged children from using the left hand. Some children were physically encouraged to move their pencil into the right hand. Naturally, left-handed children then had to practice unfamiliar movements. Their visible behavior could hide their original preference. Entire classrooms could therefore appear more right-handed than they naturally were. As these social pressures weakened, Left-handedness became more openly accepted. Today, children are generally freer to use whichever hand feels natural. Yet many everyday objects still reveal our right-handed majority. Ordinary scissors can feel surprisingly awkward when operated with the left hand. Desks, tools, and controls can also favor right-handed users. Even writing can create a small problem for left-handers. Moving across a page can leave graphite or fresh ink beneath the hand. Left-handed writers often adapt by changing paper angles, grips, or wrist positions. Adaptation is useful, but it doesn't give left-handers mysterious superpowers. Hand preference doesn't reliably determine creativity, intelligence, talent, or personality. And not everyone fits perfectly into a simple left versus right category. Our handedness reflects the combined influence of biology, development history, and evolution. Humanity overwhelmingly favors the right hand, yet the left-handed minority persists. And perhaps being rare is part of the reason the left hand never disappeared.